Imagine our observable universe shrunk down to the size of a basketball. Every galaxy we have ever seen, every star ever catalogued, the entire cosmos visible to us, all of it, compressed into a single basketball sitting on a table. Now picture the rest of the universe surrounding it. The conservative estimate from modern cosmology says the full universe is at least the size of a 20-story building. That basketball, our entire observable cosmos, sits somewhere inside it. One small ball, surrounded by a vast structure we have no way to see. And that is the conservative estimate. The less conservative estimates make it much worse. If inflation theory is correct, our observable universe is to the full cosmos what a single atom is to an entire planet. And some cosmologists think the full universe is genuinely infinite. There is more universe than you will ever be able to see. Not just a little more, vastly more, possibly infinitely more. Most of it is permanently hidden from us. We have no way to see it. We have no way to reach it. We have no way to send anything toward it that will ever arrive. It is there, real, full of galaxies and stars and structure. And we will never directly know any of it. This is one of the strangest facts in modern cosmology, and it does not get talked about much. The universe we observe is not the universe. It is a small bubble of vision, surrounded by an unreachable cosmos that extends in every direction. We know it is out there. We can prove it with measurements of geometry and uniformity. We just have no way to look at it directly. No telescope, no matter how powerful, will ever capture an image of it. No signal we send will ever cross into it. No signal from there will ever cross back. Tonight, we are going to slowly walk through this strange situation. We will look at why most of the universe is invisible to us. How we know there is more out there, even though we have no way to prove what is inside. What lies past the limits of our vision. And we will end with a quieter truth, that even what we can currently see is slowly slipping further away from us. Every second, a little more of it disappears past our reach forever. Lie back, settle in, we have time. There is a number that gets used a lot in space documentaries, and it deserves to be questioned. The number is 93 billion light-years. That is the commonly quoted diameter of the observable universe. The sphere of space we can theoretically see, centered on Earth, extending outward in every direction. Inside that sphere, there are an estimated 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. Around many of those stars are planets. Some of those planets, almost certainly, have water. Some, possibly, have life. Some, conceivably, have minds wondering about the same questions we are wondering about now. 2 trillion galaxies. That is what we can see. The number itself deserves a moment. 2 trillion. Each galaxy contains, on average, somewhere between 100 billion and 400 billion stars. If we take an average estimate of 200 billion stars per galaxy, the total number of stars in the observable universe is approximately 400 billion trillion, or in standard scientific notation, 4 times 10 to the 23. That number is roughly comparable to the number of grains of sand on every beach on Earth, multiplied by 1,000,000. Or, looked at another way, the total number of stars in the observable universe is about 10 times larger than the total number of cells in every human being who has ever lived. These are extraordinary numbers. And they describe only the bubble of the cosmos we can see. The 2 trillion figure itself comes from a study published in 2016 by Christopher Consolis and colleagues using deep observations from the Hubble Space Telescope and detailed analysis of how galaxy populations evolve over cosmic time. Earlier estimates had put the number at around 200 billion. The new study found that earlier surveys had missed many small galaxies, especially in the early universe. The true count is roughly 10 times higher than previously thought. Even so, the 2 trillion estimate has uncertainty. Some recent analyses suggest the number might be closer to several hundred billion if you only count galaxies above a certain minimum size. Others have pushed it slightly higher. 2 trillion is a useful round number that captures the order of magnitude. The actual count could be a few times more or less. But there is something strange about that number when you stop to think about it. The universe is only 13.8 billion years old. Light travels at a finite speed. The fastest signal that can ever reach us is light itself, and light moves at 300,000 kilometers per second. In 13.8 billion years, light can travel 13.8 billion light years. So how is the observable universe 93 billion light years across? The answer is the first piece of this puzzle. The light reaching us today has been traveling for 13.8 billion years, but the space it traveled through has been stretching the entire time. When that light was first emitted, the galaxy that produced it was much closer to us. By the time the light arrived at our telescopes, the galaxy had been carried away by cosmic expansion. The light traveled 13.8 billion light years. But the place it came from is now approximately 46 billion light-years away. This is the particle horizon, the furthest distance from which any light can have reached us since the beginning of the universe. Multiply that by 2, account for the fact that it works in all directions, and you get the diameter of the observable universe, roughly 93 billion light-years across. To put this in perspective, the light from the most distant galaxies we can currently observe started its journey when the universe was less than 1 billion years old. By the time it reached us, the universe had expanded so dramatically that those galaxies, if they still exist in some form, are now nearly 46 billion light-years away. We are not seeing them as they are. We are seeing them as they were, more than 13 billion years ago. Their current state is something we will never observe. This is one of the strange consequences of looking out into space. Every observation we make is also a view into the past. The light from the sun takes about 8 minutes to reach Earth. So when we look at our nearest star, we are seeing it as it was 8 minutes ago. The light from Proxima Centauri, our closest stellar neighbor outside the solar system, takes 4.2 years to arrive. We see Proxima as it was 4 years and 3 months ago. The light from the Andromeda galaxy takes about 2.5 million years to reach us. So we see Andromeda as it appeared when our ancestors were just beginning to develop stone tools. The further out we look, the further back in time we see. At the limit, we are seeing light that has been traveling for 13.8 billion years from regions of space that are now 46 billion light-years away. That is the limit of what we can ever observe through ordinary light. But there is a deeper boundary, sitting inside this one, a boundary that very few people talk about, and that matters far more for what we can know. It is called the cosmic event horizon. The cosmic event horizon is the maximum distance from which any light emitted today can ever reach us. Not light emitted at the dawn of time, like the cosmic microwave background. Not light from billions of years ago. Light leaving right now, this moment, from a distant galaxy. That distance is approximately 16 billion light-years. Anything beyond 16 billion light-years from Earth, even if it sent a flash of light directly at us this very instant, will never have that light arrive. Not in 1 million years, not in 1 trillion years. Not ever. The space between us and those galaxies is expanding faster than light can cross it. Their light is moving toward us, but the road is stretching out underneath it faster than the light can travel. Those galaxies are causally disconnected from us. We can see what they used to be billions of years ago, when their light started its journey through a smaller, slower expanding universe. But what they are doing right now, this moment, we will never know. The information is unreachable. Think about what this means. The galaxies we observe at the very edge of the observable universe, those distant smudges of light captured by the Hubble Space Telescope and the James Webb Space Telescope, the ones that look like tiny red blurs in the deepest images we have ever taken, those galaxies are visible to us only because of light they emitted long ago. The light traveled across a younger, smaller universe to reach us. But if we wanted to know what is happening at those locations right now, today, in this current moment of cosmic history, we have no way to find out. The current state of those distant galaxies is forever shrouded behind the cosmic event horizon. Their light, emitted today, will never arrive at Earth. There is a useful way to think about this. Imagine you live on the bank of a river that flows away from you, faster than you can swim. If you throw a message in a bottle into the river, the bottle will be carried away. You can never get to where the bottle ends up, because the water moves faster than you. Anyone downstream from a certain point is unreachable. Even though the water connecting you to them is continuous, and the bottles you throw still exist somewhere in that water. Cosmic expansion works like that, but in 3 dimensions and at all scales simultaneously. Space itself is flowing outward, faster than light at sufficient distances. We can throw messages into space, emit light signals, but anything past the cosmic event horizon will never receive them. Anything past this boundary will never reach us with its own messages. We are not isolated by distance. We are isolated by the flow of space itself. This is the wall. It is not a wall in the physical sense. There is nothing there. No solid surface, no obstacle. You could walk right through it without noticing anything different. Space looks identical on both sides. Physics works the same way on both sides. The wall is an information limit, not a spatial one. It marks the boundary of what we can ever know, not what exists. And here is the strangest part. The wall is everywhere. It does not just exist out there at the edge of our cosmic neighborhood. Every point in the universe has its own cosmic event horizon. Every observer, anywhere in the cosmos, is at the center of their own perfect sphere of knowability. A civilization in a galaxy 10 billion light-years away has its own observable universe, its own event horizon, its own wall. Their wall overlaps slightly with ours, but most of what is inside their bubble is outside ours, and most of what is inside our bubble is outside theirs. There is no special center to the universe. There is no edge to the universe. There are only horizons, defined by where each observer happens to be standing. Stand on Earth, and your horizon is here. Stand on a planet in the Andromeda Galaxy, and your horizon is shifted slightly. Stand somewhere we cannot see at all, in a galaxy we have no path to visit, and your horizon is somewhere else entirely. The wall is local. The wall is personal. The wall is wherever you are. The light we receive from the most distant parts of our observable universe is old, very old. We are not seeing those galaxies as they are now. We are seeing them as they were billions of years ago, when the light first started traveling. The galaxies themselves have changed since then. Some have merged with others. Some have died. Their stars burned out, their gas exhausted. We will never see those changes. We will only ever see the light that left them long ago. The current state of those galaxies, what they look like at this moment, is permanently hidden from us. The CMB, the oldest light we can detect, was emitted about 300-80,000 years after the Big Bang. It has been traveling for 13.8 billion years. The region of space it came from is now, by our best calculations, 46 billion light-years away. That radiation marks the deepest we can see. Before that, the universe was opaque. There is no information available to us from before that moment, no matter how good our telescopes become. The cosmic microwave background deserves a moment of attention because it is genuinely strange. When you look at the night sky in visible light, you see dark space with scattered points of light from stars and galaxies. But when you look at the same sky in microwave wavelengths, you see something completely different. The entire sky is glowing uniformly in every direction. It glows at a temperature of about 2.7 Kelvin, extraordinarily cold, but not zero. That glow is the cooled remnant of the heat from the early universe. It has been traveling toward us for nearly 14 billion years. When you look at it, you are looking at the youngest universe, the cosmos, as it appeared just 380,000 years after the Big Bang, when it had cooled enough for atoms to form and light to travel freely for the first time. Before that moment, the universe was a hot, dense plasma. Light could not travel through it. There was no transparency. We have no way of seeing into that earlier epoch with light, because no light from there can reach us. This ancient radiation is, in this sense, a wall of its own, a wall of opacity. Before it, the universe was hidden behind hot gas. After it, the universe was transparent. The boundary between those two states is what we observe today as the CMB. It is the oldest light in existence. So we have, in our cosmic perspective, layered horizons, each one a kind of wall. The particle horizon at 46 billion light-years, marking the boundary of what we can ever observe from any moment in cosmic history. The cosmic event horizon at 16 billion light-years, marking the boundary of what we can ever influence or be influenced by going forward. The opaque wall of the early universe at 380,000 years post-Big Bang, marking the boundary of what we can see optically. And the future visibility limit at 61 billion light-years, marking the largest the observable universe will ever become. These boundaries are not arbitrary. They emerge from the basic structure of an expanding universe with a finite age and a finite speed of light. They are consequences of physics, not limits imposed from outside. The universe is large enough, and light is slow enough, that we are inevitably trapped inside a finite bubble of perception. Even with perfect instruments and infinite time, our view is bounded. This is one of the more striking lessons of modern cosmology. Our position in the universe is not just spatially specific, it is also informationally limited. We see what we see because of where and when we happen to exist, not because the universe has chosen to reveal itself to us. We are inside a bubble of vision, surrounded by a wall we cannot cross. The universe continues beyond it. We just have no way to know it. If we have no way to see past the wall, how do we know there is anything out there? The strongest evidence is geometric. We can measure the shape of space itself, and the answer it gives us is profound. The universe is flat. Not flat like a sheet of paper exactly, flat in the geometric sense. If you draw a triangle in the universe, its three angles add up to exactly 180 degrees. If you draw two parallel lines, they remain parallel forever. never meeting and never diverging. If you measure the circumference of a circle and divide by its diameter, you get exactly pi. These are the properties of flat space. If the universe were curved like a sphere, the triangles would have angles adding up to more than 180 degrees. Parallel lines would eventually meet. Circles would have circumferences smaller than pi times their diameter. If the universe was saddle-shaped, the opposite would happen. Triangles would have angles adding up to less than 180. Parallel lines would diverge. This is not just abstract geometry. The shape of space is something we can actually measure if we have access to triangles big enough, and we do. The cosmic microwave background gives us a natural ruler. The size of the temperature fluctuations in the CMB is predicted by physics. If we know how big those fluctuations should be at the source, and we measure how big they appear in our sky, we can calculate how the space between us and them has affected their apparent size. Curved space would distort them in specific ways. Flat space would leave them undistorted. We have measured this very carefully. The Planck satellite, which mapped the CMB in extraordinary detail, gave us the most precise measurement of cosmic curvature ever obtained. The result: the universe is flat to within a margin of error of about 0.00002. That number is important. It tells us something we could not otherwise know. The Planck satellite was a European Space Agency mission that operated from 2009 to 2013, mapping the entire sky in microwave wavelengths with unprecedented precision. Before Planck, we had measurements from earlier missions, COBE in the 1990s, WMAP in the 2000s, each one improving on the last. Planck represents the current state of the art. Its data is what cosmologists use today to derive the basic parameters of our universe. The flatness measurement is one of those parameters, and it is striking how flat the universe appears to be. If you draw a very large triangle in space, large enough that one side spans most of the observable universe, its angles add up to within 0.02% of 180 degrees. That is essentially perfectly flat, to within our measurement precision. If the universe is curved, the curvature has to be very, very gentle. So gentle that across the entire observable universe, 93 billion light-years across the curvature, is not detectable. This is like standing on a small patch of the Earth. From close up, the ground looks flat. The curvature of the planet is not visible to your eyes. You would need to climb very high or look across great distances to detect that the surface is actually curved. Think about that. The Earth has a circumference of about 40,000 kilometers. From a typical viewpoint on the ground, the horizon looks flat. The curvature of the planet is too gentle to perceive directly. You would need to fly up in an airplane, or sail far out to sea, or look at the shape of the planet's shadow on the moon during a lunar eclipse, to detect that the ground is actually curving away beneath you. The universe has, by analogy, an enormous circumference, if it has one at all. Our entire observable bubble is the equivalent of a flat patch of ground on a planet so large we have no way to perceive its curvature. The planet might be Earth-sized, or it might be the size of the solar system, or it might be infinite. We are stuck on our small patch, unable to see far enough to tell. What this means is one of two things. Either the universe is genuinely perfectly flat, extending forever in every direction with no curvature at all, or the universe is curved, but immensely larger than what we can see. So large that the curvature is too gentle to detect at our scale of observation. Either possibility tells us the universe is much bigger than the observable portion. If it is flat and infinite, then by definition it is infinitely larger. If it is curved but undetectably so, then it must be at least hundreds of times larger. There is a second argument for a much larger universe related to the cosmic microwave background. The CMB is remarkably uniform. The temperature is almost the same in every direction, no matter where we look. The variations are tiny, about 1 part in 100,000. The hottest spots in the CMB and the coldest spots differ by only a tiny fraction of a degree. This uniformity is, on the face of it, surprising. The CMB photons we see today come from regions of the universe that, in the standard Big Bang model, without inflation, should never have been in causal contact with each other. Two patches of CMB on opposite sides of our sky, patches whose light we are now receiving, are about 90 billion light-years apart by current proper distance. In a universe only 13.8 billion years old, those two patches should never have had time to exchange information. They should have wildly different temperatures, set by whatever local conditions existed in each region at the moment of the Big Bang. Instead, they have the same temperature, almost exactly, to within 1 part in 100,000. How can two regions that have never been in contact have such precisely matching properties? This is called the horizon problem, and it is one of the major motivations for inflation theory. Inflation provides one possible answer. The regions were in contact briefly in the very early universe before inflation pushed them apart to their current locations. During that brief pre-inflation period, the regions equilibrated. Their temperatures matched. Then, inflation drove them apart by a factor of 10 to the 26 or more, and they have been receding from each other ever since. If inflation is correct, the universe is much larger than what we observe. The regions of the CMB that should not have matched, but do, are evidence that the universe extends well beyond our current visible region. The whole inflated universe is far bigger than what we see. This is the second strong argument for an enormous, unobservable cosmos. The first is flatness. We have no way to detect curvature, suggesting the universe is much bigger than our scale of observation. The second is uniformity. The CMB is too consistent to have been set up by local processes alone, suggesting some mechanism, probably inflation, connected our observable region to a much larger context. Both arguments converge on the same conclusion. The universe is vastly larger than what we can see. We cannot prove it directly. We can prove it indirectly through the consequences of its size manifesting in the small patch we do see. In 2011, 3 physicists named Mihran Vardanyan, Roberto Trotta, and Joseph Silk published a paper that put a specific number on this. Using a statistical technique called Bayesian model, averaging a way of combining the predictions of multiple cosmological models, weighted by how well each fits the data they calculated, a conservative lower bound on the size of the universe. The Bayesian approach is worth a moment of explanation. Most statistical methods ask, given my model, how well does it fit the data? Bayesian model averaging asks something different. Given my data, which of my possible models is most likely to be correct? It is a form of statistical reasoning that combines evidence across multiple hypotheses rather than committing to a single one. For the size of the universe, this approach combines estimates from different cosmological assumptions: closed universe, flat universe, open universe, weighted by how well each model fits the observed data. The result is a probability-weighted estimate rather than a single committed answer. The result? The total universe must be at least 250 times larger than the observable part. 250 times. That sounds like a number you can imagine, but think about what it means. The observable universe is 93 billion light-years across. Multiply by 250. The total universe is at least 23 trillion light-years across. If you have made it this far in the video and find this interesting, or if it is helping you wind down for sleep, consider hitting the like button or subscribing. The algorithm uses those signals to know what kind of audience wants long-form, calm content like this. It costs you nothing. It helps me keep making these videos. Now, back to the cosmos. If we were to picture the entire universe at the size of Earth, the observable part, everything we can see, every galaxy we have ever mapped, every star we have ever named, would be roughly the size of a grain of sand. A single grain, lying somewhere on the surface of the planet. The rest of Earth, everything beyond that single grain, is what we cannot see. Let that comparison sit for a moment. Every galaxy you have ever heard of, the Milky Way, Andromeda, the galaxies in the Virgo cluster, the distant galaxies imaged by the James Webb Space Telescope, every spiral, every elliptical, every irregular galaxy, in every catalogue ever compiled, they are all in that grain of sand. 2 trillion galaxies in a single speck of dust. And around that speck, the rest of Earth, full of additional unobservable cosmos. This is the conservative estimate. Let me say that again. This is the cautious answer, the minimum. The less conservative estimates run much, much larger. Inflation theory. The idea that the early universe expanded by an enormous factor in the first fraction of a second after the Big Bang predicts a universe that is far larger than the 250 times figure. Inflation theory was proposed in the 1980s by Alan Guth and refined by many physicists since. The idea is that during a period lasting from roughly 10 to the minus 36 seconds to 10 to the minus 32 seconds after the Big Bang, the universe underwent an extraordinary period of expansion. In that fraction of a second, space expanded by a factor of at least 10 to the 26. That is 1 followed by 26 zeros. A single proton-sized region of space would, in that brief moment, have grown to be larger than the entire currently observable universe. Inflation solves several problems in cosmology that are otherwise difficult to explain. It explains why the universe appears flat. It explains why the cosmic microwave background looks uniform in every direction, even though regions on opposite sides of our sky should never have been in causal contact in the Standard Model. It predicts the kind of tiny temperature fluctuations in the CMB that we actually observe, which later grew into the structure of galaxies and clusters we see today. But inflation has an implication that is rarely emphasized in popular accounts. If inflation is correct, the total universe is vastly larger than what we observe. We see only a tiny patch of the cosmos that was inflated during that early moment. The rest of the inflated region extends far past our horizon. According to most inflation models, the universe could be 10 to the 23 times larger than the observable portion. That number, 10 to the 23, is a 1 followed by 23 zeros. There is no human analogy for it. There is no useful way to picture it. It is simply a number that means, for any practical purpose, infinite. If the inflationary models are correct, the observable universe is to the total universe what a single atom is to an entire planet. We are an unimaginably small island of vision floating in a cosmos that is, for all intents and purposes, boundless. And there is a third possibility, which is that the universe is genuinely, mathematically infinite. In an infinite universe, the question, how big is it, has no answer. It has no edge anywhere, in any direction. It just goes on, forever. Many cosmologists consider this the most likely scenario. Not because we have proof, but because the alternatives require fine-tuning. A finite universe needs to have a specific size, set by some unknown mechanism. An infinite universe just is. There is nothing to explain. Imagine the possible answers to how big is the universe as a kind of probability distribution. The smallest possible value is the observable universe itself, 93 billion light-years across. The next plausible value is the 250 times estimate 23 trillion light-years. Then there are the inflation-based estimates ranging from 10 to the 23 times to almost arbitrarily large. And at the upper limit, infinite. Across this entire range of possibilities, the universe is somewhere. We do not get to choose which one is true. Nature has already chosen. We just have not been able to measure precisely which choice was made. The discovery of this strange situation is relatively recent. For most of human history, no one knew the universe extended beyond what was visible. The night sky looked like a fixed dome of stars, and the cosmos was assumed to be roughly equivalent to what could be seen. Even in the early 20th century, most astronomers thought the Milky Way was the entire universe. The Andromeda galaxy was just a fuzzy patch in the sky, and there was debate about what it actually was. Was it a nebula inside the Milky Way? Or was it a separate island universe, a whole other galaxy located far outside our own? The question was settled in 1924 by Edwin Hubble, who used the Mount Wilson telescope to identify Cepheid variable stars in Andromeda. By measuring how those stars appeared, he could calculate their distance. Andromeda turned out to be far outside the Milky Way, over 2 million light-years away. It was, indeed, a separate galaxy. The universe was suddenly much larger than anyone had thought. In the years that followed, Hubble and other astronomers discovered that the universe contained millions of galaxies, then billions. They also discovered that those galaxies were moving away from each other. The universe was expanding. Tracing the expansion backward led to the idea of the Big Bang, the moment when the universe began. By the mid-20th century, the basic picture was in place. The universe was vast, expanding, and had a finite age. It contained billions of galaxies. The light from the most distant of them had been traveling for nearly the entire age of the universe. But there was still no clear understanding of how large the universe actually was, beyond what we could observe. That question only became sharply defined when cosmic microwave background measurements gave us detailed data on the universe's geometry, and when statistical methods like Bayesian model averaging were applied to estimate lower bounds, we have known there was an observable universe, distinct from the total universe, for less than a century. The cosmic event horizon, the deeper boundary, marking what we can ever observe even in the future, was not fully appreciated until the discovery of dark energy in the late 1990s. Our understanding of the size and structure of the cosmos is, in historical terms, brand new. Earlier generations did not know about most of this. Future generations, as we discussed, will know less. We exist in a strange moment when the universe has revealed enough of itself for us to ask these questions, but not enough for us to answer them definitively. The question, how big is the universe, might be permanently unanswerable. We can put lower bounds on it. We can speculate about upper bounds. But the actual answer, if the universe even has a single specific size, may not be accessible to any observation we can ever make. That is, in a way, the central fact of modern cosmology. We know enough to understand our limits. We do not know enough to overcome them. The wall is not just a vision problem, it is a reachability problem. Imagine you set out today, traveling at the speed of light, in a perfectly straight line. Light is the fastest anything can move in our universe. Nothing, not even information, can travel faster. So you are doing the absolute maximum possible. This is, of course, physically impossible. Nothing with mass can travel at the speed of light. Even getting close to it requires impossible amounts of energy. But let us suspend that concern for a moment. Pretend you are a beam of light or a massless particle or some hypothetical traveler that can move at the universal speed limit. You set out from Earth. You head outward in any direction. You travel for as long as you need to. For the first few billion years of your journey, you would make progress. The space between you and your destination would stretch a little, but you would still be moving forward faster than the stretching. After a long enough time, you would arrive somewhere. But there is a distance beyond which this fails. The cosmic expansion is accelerating. Dark energy, whatever it is pushing space apart faster and faster. At a certain distance from Earth, the rate at which space is stretching exceeds the speed of light. Anything beyond that distance is moving away from us faster than light can move toward us. We cannot catch up. Even traveling at the universal speed limit, we would never close the gap. That distance is about 16 billion light-years today. The cosmic event horizon, anything currently inside 16 billion light-years from Earth, we could theoretically reach if we left right now and traveled at the speed of light. Galaxies, stars, planets, all of them are inside our potential reach, even if it would take billions of years to get there. The total number of galaxies inside our reachable bubble is approximately 66 billion, a small fraction of the trillions we can see. Anything beyond 16 billion light-years we will not reach. Not us, not any descendants we might have, not any civilization that arises in the future and tries to expand outward. Those distant galaxies are permanently past any practical reach. The space between them and us grows every second, faster than any signal can cross. There is something worth dwelling on here. We are accustomed to thinking that given enough time, anything is reachable. If a star is 1,000 light-years away, it takes 1,000 years of light speed travel to get there. If a galaxy is 1,000,000 light-years away, it takes 1,000,000 years. The relationship seems linear, predictable. Travel takes time, but distance and time are commensurable. The journey may be long, but it can be calculated. This intuition breaks down at cosmic scales. Beyond a certain distance, the relationship between time and reachability stops being linear. It becomes asymptotic. You can travel forever, at the maximum possible speed, and still never arrive. The destination keeps moving away from you, faster than you are moving toward it. It is not just that the journey takes a long time. The journey cannot be completed at all. The distance between you and your target is increasing without bound. Every second, the gap widens. Even at light speed, you fall further behind. This is one of the more unsettling facts in modern cosmology. We can see things we cannot touch. The most distant galaxies in our observable universe are visible, their old light still reaching us, but they sit forever outside any path. We are looking at them across a gap that cannot be closed. They have already, in a sense, said goodbye to us. We just have not noticed. And the gap is growing. Right now, today, the future visibility limit is around 61 billion light-years. That is the maximum distance from which any light emitted at any point in cosmic history can ever reach us. It is slightly larger than our current observable universe of 46 billion light-years in radius, because some light from regions beyond our current view is still on its way to us. It will arrive in the deep future. Within the future visibility limit, there are about 4.7 trillion galaxies in total. We can currently see 2 trillion of them. The other 2.7 trillion are out there, emitting light right now, with that light slowly making its way toward us. Over the next many billions of years, those galaxies will gradually come into view as their light finally arrives. But that is the absolute maximum. The future visibility limit is fixed. The universe can never reveal more to us than what lies within 61 billion light years. Beyond that, we will not see anything, ever. To understand why, think about what happens to light emitted from very distant regions. Imagine a galaxy currently sitting at, say, 80 billion light years from us. That galaxy is inside the unobservable universe. It is beyond our particle horizon. If it emits a flash of light right now, where does that light go? The light tries to travel toward us at the speed of light. But the space between us and that galaxy is expanding very fast. Faster than the light can cross. The light moves forward, but the road stretches faster than the light moves. The light makes progress, but the destination moves away faster. Over billions of years, the light gets stretched into longer and longer wavelengths. Its frequency drops, its energy decreases. Eventually, it becomes undetectable, even in principle. The light loses the race. That galaxy will never appear in our skies. No matter how patient we are, no matter how advanced our instruments become, the light cannot reach us. It was emitted toward us, but the cosmos itself is carrying the galaxy away faster than the light can return. This is true for all galaxies currently past approximately 16 billion light-years. Their present moment light cannot reach us. But here is the subtle distinction. Some of those galaxies emitted light long ago when they were much closer to us in proper distance. Light that left them when the universe was younger and smaller might still be on its way to us. That older light, from regions that are now beyond reach, is what we observe today. We see them as they were billions of years ago when their light first started its journey. Their current state is invisible to us. Their future is invisible to us. We see only their distant past. And the difference between 61 billion and 16 billion between what we can see and what we can reach represents an extraordinary gap. There are trillions of galaxies inside the future visibility region that we can observe but never visit. We can map them. We can photograph them. We can study their composition and motion. But we have no way to ever go there because the space between us and them is stretching faster than we could ever cross. In a sense, we are at a unique moment in cosmic history. The universe is, right now, in a state where we can see far more than we can reach. We can know far more than we can interact with. We are observers of an immense cosmos that is forever beyond our touch. It is a strange position to be in. Not unlike standing on a mountain looking down at a landscape we will never walk through, we can describe it, we can admire it, we can never visit it. To make this more concrete, consider some specific examples. The Boötes void is one of the largest known empty regions in the universe, a roughly spherical area about 330 million light-years across, with very few galaxies inside it. The Boötes void is located about 700 million light-years from Earth. It is well within our observable universe, well within our reachable region. If we had infinite time and could travel at light speed, we could go there. We could investigate why it is so empty. We could explore its interior. But other voids beyond 16 billion light-years, are permanently past our reach. They exist. We can observe some of them through the CMB's subtle imprints, but we cannot go to them. They are permanently external to anything we can do. Or consider quasars, the bright cores of distant galaxies powered by supermassive black holes feeding on gas. We have observed quasars at distances of more than 13 billion light-years. The light from those quasars left them when the universe was only a few 100 million years old. We see them as they appeared in the very early universe. But where are those quasars now? They have evolved. The black holes that powered them may have grown or merged with others. The host galaxies have changed. They might not even be visible anymore, their gas supply exhausted, their black holes dormant. Or they might. We do not know. The current state of those distant quasars is unobservable. We see only their distant past. Whatever they are doing today, in this moment, is locked behind the event horizon. The signal cannot reach us. This applies to everything past a certain distance. The Andromeda galaxy, our nearest large galactic neighbor, is only 2.5 million light-years away. When we look at it, we are seeing it as it was 2.5 million years ago. Andromeda has changed in those 2.5 million years. Stars have been born. Stars have died. The galaxy has rotated. It has moved closer to us, but those changes are not yet visible. We are looking into Andromeda's past. The Sombrero galaxy, in the Virgo cluster, is about 30 million light-years away. We see it as it was when ancient mammals first appeared on Earth. Whatever the Sombrero is doing now, we will not see for another 30 million years. NGC 1300, a beautiful barred spiral galaxy, is about 61 million light-years away. We see it as it was when dinosaurs roamed our planet. These delays compound as we look further out. The most distant galaxies imaged by the James Webb Space Telescope are seen as they appeared when the universe was less than 500 million years old. We are looking at the very beginning of galaxy formation. Those galaxies have, by now, evolved into something completely different, possibly disappeared, possibly merged with others, possibly grown into modern galaxies. We see only their infancy. The universe we observe is not a snapshot of the present. It is a layered record of the past, with different distances showing us different cosmic eras. The further out we look, the further back we see. And the further out we look, the more those distant places have changed since their light left them. We are surrounded by a cosmos that we observe in its past, can never reach in its present, and will lose entirely as it recedes into the inaccessible future. There is a useful word for this kind of relationship: causally disconnected. Two regions of space that cannot exchange signals in either direction are described this way. They might as well not exist from each other's perspective. Information cannot cross between them. Influence cannot propagate. Whatever happens in one cannot, even in principle, affect the other. The unobservable cosmos is causally severed from us. Whatever happens out there will happen without us. Whatever happens here will happen without them. We share a cosmos, but we share nothing else. We have established that there is more universe past what we can see, much more, possibly infinite more. The natural question is, what is out there? The answer, based on everything we understand about physics, is straightforward and deeply strange. It is more of the same. Galaxies, stars, planets, cosmic voids, filaments of dark matter weaving the structure of space. The same kind of cosmos we see in our observable bubble, just continuing on. There is no reason to think the universe is different beyond our horizon. Every measurement we have taken suggests the universe is uniform in its large-scale properties. The same physical laws, the same particles, the same parties, the same patterns of structure formation. This is called the cosmological principle, the idea that the universe on the largest scales looks the same everywhere. We have no way to prove this for the unobservable portion. But it would be very strange if the physics suddenly changed at the boundary of our vision. Far more likely is that the universe continues on, behaving as it does here for as far as it extends. The cosmological principle has two parts. The first is homogeneity, the idea that the universe, averaged over very large scales, has the same density of matter and energy everywhere. The second is isotropy, the idea that the universe looks the same in every direction. Both of these properties have been carefully tested with cosmic microwave background measurements and galaxy surveys, and both appear to hold to excellent precision across our entire observable region. If the cosmological principle is correct, then by symmetry, the regions of space beyond our horizon should be statistically similar to the regions inside our horizon. The same average density of galaxies, the same distribution of cosmic structures, the same kind of large-scale environment. There might be local variations, clusters of galaxies, cosmic voids, filaments of dark matter, just as there are in our observable region. But the overall character of the universe should be consistent. Let us try to picture this. Imagine zooming out from our observable bubble. At first, you see what we see: galaxies arranged in a vast cosmic web. Long filaments of galaxies, separated by enormous empty voids, all of it connecting into a frothy three-dimensional pattern that looks something like the structure of a sea sponge or the foam in a cappuccino. Galaxies cluster at the intersections of filaments. Voids occupy the spaces between. The whole structure is organized at scales of hundreds of millions of light years. Now zoom out further past the edge of our observable region. What you would see, if you could see it, is more of the same pattern. More filaments, more voids, more galaxy clusters. More of the cosmic web continuing in every direction. It does not look different beyond our horizon. It looks the same, just as much, just continuing. The largest known structures in the observable universe are extraordinary in their own right. The Sloan Great Wall is a sprawling complex of galaxy superclusters, about 1.4 billion light-years long, located approximately 1 billion light-years from Earth. It contains thousands of galaxies arranged in a sheet-like structure. The Hercules Corona Borealis Great Wall, discovered through gamma-ray burst observations, is even larger, possibly stretching 10 billion light-years across. Though this is contested, and some studies suggest it may not be a real structure at all, but a statistical artifact. Whether or not the very largest claimed structures are real, the observable universe is genuinely full of immense arrangements of matter. The Laniakea supercluster, our own local supercluster, is about 500 million light-years across and contains over 100,000 galaxies. Even Laniakea is small compared to some of the more extreme structures in our cosmic neighborhood. These vast structures exist within our observable universe. They are visible. We can map them. But they also continue beyond our horizon. The Sloan Great Wall, the Laniakea supercluster, the various great walls and filaments, these are likely just nearby examples of structures that pervade the entire universe. Past our horizon, there are more great walls, more superclusters, more filaments. The cosmic web continues, in the same general pattern, throughout whatever larger universe exists. Zoom out further still. The pattern keeps going. Filaments and voids, clusters and superclusters, all repeating their structure at the same general scale. There is no edge. There is no obvious boundary where things change. There is just more cosmic web extending in every direction as far as the universe goes. This is the picture we get from our best cosmological models combined with the cosmological principle. The universe is, on the largest scales, statistically uniform. The same general kind of structure, repeats throughout. There is no privileged region, there is no center. So past the wall, there are more galaxies. Hundreds of billions of them. Trillions, possibly an infinite number, depending on which estimate you trust. Each galaxy contains hundreds of billions of stars. Around many of those stars, planets. On some planets, conditions might be right for life. On some, life might have arisen and evolved and developed intelligence. On some, civilizations may exist right now, looking out at their own night sky, wondering what is out there. They will remain unknown to us. We can never communicate with them. They are real, almost certainly, but they are forever hidden to us. Think about that for a moment. Somewhere out there, in a region we will never observe, there is almost certainly a planet not unlike Earth. Liquid water on its surface, an atmosphere rich enough to support complex chemistry, continents and oceans possibly, beings of some kind, conscious or not, going about their existence. If life is even moderately common in the universe, and our current best guess is that it is at least possible on any number of worlds, then beyond our horizon there are countless instances of it. Most of them we have no path to knowing about. Most of them we have no way to confirm even exist. This is not an unscientific claim. It is a statistical implication of the size of the universe combined with the basic principles of physics. If the cosmos is large enough, and the chemistry of life is allowed by the laws of nature, then life almost certainly exists in many places we cannot see. And consider the spectrum of variation. In our local universe, we observe galaxies in many different stages of evolution. Young galaxies still forming stars at high rates. Mature galaxies with stable stellar populations. Old galaxies that have used up most of their gas and are slowly fading. Galaxies that have collided with others, leaving behind tidal streams and disturbed spiral arms. Galaxies that contain active, supermassive black holes at their centers, blazing as quasars. Galaxies that are dormant, their central engines quiet. Galaxies of every size, from massive ellipticals containing trillions of stars to dwarf galaxies with only a few million. Past our horizon, this entire spectrum exists, repeated trillions or quadrillions or infinitely many times. There are galaxies at every stage of evolution. There are exotic galaxies of types we have not even observed in our own cosmic neighborhood. There are emerging systems, dormant systems, young systems, dying systems. There are clusters of galaxies with thousands of members. There are isolated galaxies in cosmic voids. There are environments of every kind we can imagine, and probably some we cannot. And around these galaxies, planets. Trillions of planetary systems scattered across the unobservable cosmos. Some hot, close to their stars, some cold, far from any source of warmth. Some in the so-called habitable zone, where liquid water could exist on a planetary surface. Some too small to hold an atmosphere. Some larger than Jupiter, gas giants in their own right. In our local cosmic neighborhood, we have begun to identify thousands of these planets. The Kepler Space Telescope discovered thousands of exoplanets around nearby stars during its operational life. The James Webb Space Telescope and other instruments continue this work. We now know that planets are common. Most stars likely have at least one planet. Many have several. The total number of planets in our observable universe is enormous, possibly more planets than there are stars, considering that some stars have multiple planetary companions. Multiply this across the unobservable cosmos. Whatever the total size of the universe is, planets are everywhere. In every Hubble volume, there are countless planets. In every imaginable cosmic environment, There are worlds going through their own histories of formation, evolution, and eventual decay. Some of these planets, almost certainly, have the right conditions for life: liquid water, a stable atmosphere, energy sources, the right combinations of chemical elements. Life requires a specific set of conditions, but those conditions are not exotic. They occur naturally on planets across the cosmos. Given the sheer number of planets that exist, life almost certainly arises in many places. Some of those life-bearing planets may have evolved complex life, multicellular organisms, diverse ecosystems, intelligent species, perhaps even civilizations capable of looking up at their own night sky and asking the same questions we are asking. Most of them we have no way of knowing. They are beyond our horizon. Their light cannot reach us. Their signals cannot reach us. They exist. They think. They wonder, and to us, they might as well not exist at all. The cosmos contains them. We just cannot perceive them. There is a strange poetic quality to this situation. The universe is, by its sheer size, a guarantee that we are not alone. Statistical certainty replaces speculation. In a sufficiently large cosmos, and ours appears to be sufficiently large, life is not a rare event. It is a common occurrence, repeated across countless worlds. We are not unique. We are not the only example. We are not the only audience, but we are isolated. The same vastness that guarantees our company also ensures we cannot meet our companions. The expansion of space pushes them away faster than any signal can cross. The cosmic event horizon walls them off from us. The structure of the universe is such that consciousness is common and contact is impossible. This is, in a way, the deepest fact about our cosmic situation. We are surrounded by minds we have no way to get to. We are members of a community we cannot join. We are part of something vast, populated, and ongoing, and we have no way to participate in it beyond our local bubble. The numbers, if you try to take them seriously, become difficult to comprehend. Take the conservative estimate. The universe is at least 250 times larger than the observable portion. Volume scales as the cube of linear size, so the total volume of the universe is at least 250 cubed times the volume we can see. That is approximately 15.6 million times the observable volume. The observable universe contains 2 trillion galaxies, multiplied by 15.6 million. The total universe contains at least 31 quadrillion galaxies. That is 31,000 trillion galaxies, most of them forever invisible to us. If you tried to map every galaxy in the universe, even the conservative estimate, you would have to map 31 quadrillion of them. Even at 1 galaxy per second, it would take 1 billion years just to count them. The actual number is almost certainly far higher, and the larger estimates make these numbers look small. If the inflationary estimate is correct, 10 to the 23 times the observable universe by linear size, then the volume is 10 to the 69 times what we can see. The total number of galaxies becomes a number with about 70 zeros after it. It is meaningless. There is no way to picture it. There is no comparison from human experience that fits. To put that in some kind of perspective, there are roughly 10 to the 80 atoms in the entire observable universe. The number of galaxies in an inflation-sized cosmos approaches the number of atoms in everything we can see. Each galaxy contains roughly 10 to the 11 stars. Each star contains roughly 10 to the 57 atoms. So inside an inflationary scale universe, the number of stars alone is 10 to the 80, comparable to the atom count of the observable universe. These numbers do not behave like ordinary numbers. They behave like infinities that happen to have a finite value attached to them. If the universe is infinite, the question of how many galaxies exist has no finite answer. There are infinite galaxies, infinite stars, infinite planets. And here is where the strangest implication arises. In an infinite universe, or even in a very large but finite one, statistical certainty becomes a serious mathematical concept. Given enough volume, every possible configuration of matter that physics allows must occur somewhere, not metaphorically, not poetically, mathematically. If there are infinite galaxies, then somewhere out there is a galaxy identical to the Milky Way. Not similar, identical. Same arrangement of stars, same spiral arms, same supermassive black hole at its center. In that galaxy, somewhere, is a star identical to our own. A yellow main sequence star about 4.6 billion years old with the same mass and composition. Around that star is a planet identical to Earth. Same continents, same oceans, same atmospheric composition. On that planet, in this exact moment, someone identical to you is doing exactly what you are doing. Listening to a documentary about the unobservable universe, lying in bed, possibly, thinking about the strange implications of infinite space. This is not a parallel universe. This is not a multiverse. This is this universe, the same one we live in, just the parts we cannot see. The argument is sometimes called the Tegmark argument, after the physicist Max Tegmark, who articulated it most clearly. In an infinite cosmos with finite physics, repetition becomes inevitable. Not might happen, must happen. The math forces it. The logic is straightforward. The laws of physics allow only a finite number of distinct configurations of matter within a region of given size. The reason is, quantum mechanics, at the smallest scales, properties are discrete, not continuous. A region of space, the size of our observable universe, can be in one of a sprawling but finite number of possible quantum states. The number is unimaginably large, roughly 10 to the 10 to the 122 distinct states, but it is finite. To grasp how this works, consider the basic principles of quantum mechanics. At the smallest scales, the universe is not continuous. Particles do not have arbitrary positions or velocities. Instead, they have discrete quantum states, defined by a finite set of possible values. An electron in an atom can be in a specific energy level, not in any energy level. The states of particles are countable, not continuous, when properly described by quantum theory. Multiply this discreteness across all the particles in a region of space, and you get a finite total count of possible configurations, vast beyond imagination, but finite. The number is what it is limited by the finite number of particles in the region and the finite number of states each particle can occupy. If you have an infinite universe, you have infinite regions of that size, and each region has to be in one of the finite number of possible states. By pigeonhole logic, regions must repeat. There are not enough distinct configurations to fill infinite space with all different patches. Eventually, configurations recur. With infinite space, every possible configuration recurs infinitely many times. This is the quiet horror of an infinite universe. We are not alone. We never have been. There are versions of us, of our planet, of our civilization, scattered across an infinity we cannot touch. They exist. They are real. We will never know them. They have no way to know us. How far away is the nearest copy of you, according to this argument? Tegmark calculated that the nearest identical observable universe, a region of space exactly like ours, containing copies of every galaxy and every person, would be approximately 10 to the 10 to the 118 meters away. That number is so large that writing it out is meaningless. It is essentially infinite from our perspective, but it is technically finite. The copy is somewhere at some specific distance. We just can never get there. Closer than that, but still impossibly far, would be copies that are nearly identical to us but with small variations. Versions where the choices you made yesterday went slightly differently. Versions where the chair you are sitting in is a different color. Versions where you are doing something different in this moment. The closer to your actual configuration, the rarer the copy and the further away it sits. But all of them are out there in an infinite universe. All of them mathematically required to exist. It is not science fiction, it is the implication of the geometry and statistics of the cosmos we live in. Of course, this argument depends on the universe actually being infinite, or at least extraordinarily large. If the conservative 250 times estimate is correct, the universe might still be too small for these exact repetitions to be statistically guaranteed. But the larger the universe, the more certain it becomes. And at the scale of inflation predictions 10 to the 23 times, the argument starts to hold even under stricter conditions. There is a less extreme version of this thought that holds even for a more modestly sized universe. In a universe 250 times larger than what we observe, there might not be an exact copy of Earth, but there will be many, many planets similar to Earth. Many planets with continents and oceans, many planets with conditions for life, many planets with conscious beings. The exact repetitions require an infinite universe. The approximate repetitions only require a large one. Whichever version of the argument we accept, the implication is similar. We are not unique in the universe. Our existence is not a one-time event. The configuration of matter that makes up Earth, makes up us, makes up our civilization, is replicated exactly or approximately across a cosmos we cannot touch. There are countless variations on the theme of us, scattered through space we cannot visit. Think about what this does to questions of identity and uniqueness. We tend to think of ourselves as singular beings. There is one me, there is one you, there is one Earth, one Milky Way, one civilization. But in a sufficiently large universe, this is not true. There are many of each of us, many Earths, many civilizations. The cosmos produces variations on the basic theme, and given enough room, it produces all possible variations. In a way, this is liberating. We are not the only chance the universe has at consciousness. We are not carrying the entire weight of meaning by ourselves. If something terrible happens to Earth, if our civilization ends, if our species disappears, there are other configurations of matter elsewhere in the cosmos producing similar consciousness, similar civilizations, similar awareness. The flame, in some sense, continues. In another way, this is unsettling. We tend to value our uniqueness. The idea that we are one of countless copies scattered across an unreachable infinity can feel diminishing. Our specific lives, our specific choices, our specific moments, they are not as special as they feel from inside. They are repeated somewhere, in someone else's life, with someone else's mind experiencing them. This is a strange situation to be in. We are alone in our practical lives. We cannot meet our doppelgangers, cannot communicate with them, cannot even verify they exist. But we are not alone in the larger sense the cosmos is, statistically, packed with versions of us, doing variants of what we are doing, in places we will never reach. Cosmologists generally try not to make too much of the philosophical implications of this. The doppelganger argument is real, but it is also speculative. It depends on assumptions about the size of the universe that we have no way to test directly. It also depends on the cosmological principle continuing to hold at unreachable scales, which we have no way to verify. But within the assumptions we work with, the conclusion follows. A large enough universe produces copies of itself. We exist many times over. We have neighbors we cannot meet. The honest summary is that past the wall, there is almost certainly more universe than we can imagine. Possibly so much more that the words more and much lose meaning. Possibly infinite. And in that infinity, the mathematics guarantees neighbors we have no way to meet. The cosmos, as we currently understand it, is structured in a way that produces unreachable copies of itself. We are one of those copies, viewed from elsewhere. There are others, viewed from here. The universe is much stranger than the observable portion suggests. There is a useful concept that cosmologists use to think about this. It is called the Hubble volume. A Hubble volume is, roughly, a sphere of space, the size of the observable universe, about 93 billion light-years across. The cosmos can be thought of as containing many Hubble volumes, each one cut off from the others by cosmic expansion. Each Hubble volume contains its own observer perspective universe. From the center of each Hubble volume, that observer can see a particular bubble of cosmos. Galaxies inside the bubble are visible. Galaxies outside it are not. The boundaries of each Hubble volume overlap with adjacent ones. They are not strictly separate, but each observer sees only their own bubble. In an infinite cosmos, there are infinite Hubble volumes. In the 250 times larger estimate, there are about 15.6 million of them. In the inflation estimate, there are 10 to the 69th of them, each one a separate bubble of vision, centered on whatever observer happens to be at its middle. Across all those Hubble volumes, the same physics applies, the same laws, the same particles, the same forces, the same approximate distribution of galaxies, stars, and planets. But the specific configurations vary. Some Hubble volumes contain regions of higher galaxy density. Some contain larger cosmic voids. Some have produced more star systems with planets. Some have produced fewer. Some almost certainly contain life. Some do not. The total number of life-bearing planets in the universe, summed across all the Hubble volumes, is potentially astronomical. If even a small fraction of stars host planets, and a small fraction of planets host life, and a tiny fraction of life-bearing planets host intelligence, and the universe contains anywhere from millions to infinite Hubble volumes, then the total number of intelligent species in existence right now is large beyond comprehension. We are alone in our Hubble volume, in some practical sense. We have not detected any other intelligent species in our reachable region. Maybe there are some out there in the parts of our observable universe we have not searched yet. But we are unable to communicate with anything beyond our local cosmic neighborhood, and certainly not with anything past our event horizon. The aliens of distant Hubble volumes are real, almost certainly. They are also forever beyond our reach. This is what it means to live in an enormous cosmos. We have neighbors we cannot meet. We have companions in consciousness scattered across an unreachable infinity. We are not unique. We are also not connected. It is, in a way, the deepest form of loneliness available in this universe. Not the loneliness of being alone, but the loneliness of being surrounded by company you can never reach. There is something worth noting about this. Most discussions of cosmic loneliness focus on the question of whether life is rare or common. If life is rare, we might be alone in our observable universe. If life is common, we are not alone, but we are still unable to contact most of it. Either way, we end up isolated in practice. What the unobservable universe adds to this picture is a kind of certainty. Beyond a certain size threshold, the question of, are we alone, becomes meaningless. The universe is so large that it must contain other observers somewhere. The math forces it. We just cannot reach any of them. In other words, the unobservable universe makes a certain kind of company guaranteed and a certain kind of contact impossible. It is a strange and specific form of cosmic isolation. We have neighbors, but we cannot meet them. We are not unique, but we are alone in our particular bubble of perception. Some philosophers and physicists have written about the existential implications of this. We are, in some sense, members of a cosmic community that has no communication channels. There is no way for us to know what our distant neighbors are thinking about, working on, or experiencing. There is no way for them to know about us. We exist in parallel, sharing a cosmos but nothing else. This is the kind of thing the universe forces us to confront once we begin to think seriously about its scale. We are not the protagonists of a story. We are not the audience of a performance. We are one observer among many, in a cosmos vast enough to contain numerous observers, but structured in such a way that none of us can meet. There is one more thing to discuss tonight, and it is the saddest piece of this story. The universe we can see is shrinking, not physically. The universe is not getting smaller in any meaningful sense. Space is still expanding. Galaxies are still spreading apart. But the portion of that universe accessible to us, the part we can observe, is gradually decreasing. Every second, a little more of it slips beyond our reach. The reason is dark energy. Dark energy is the name we give to whatever is causing the expansion of space to accelerate. We do not fully understand it. We can measure its effects, but we cannot explain its origin. Whatever it is, it pushes space apart, and it does so more vigorously every year. The expansion rate, instead of slowing down as gravity tries to pull matter back together, is speeding up. Has been speeding up for billions of years. Will continue to speed up indefinitely. The discovery of accelerating expansion was one of the most surprising results in modern cosmology. In 1998, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, published papers showing that distant supernovae appeared fainter than they should be in a universe that was decelerating. The data was consistent with an expansion that was speeding up over time, not slowing down. This was so unexpected that initially many cosmologists doubted the result. But over the following years, additional observations confirmed it. The universe is accelerating. Something dark energy is causing this. We still do not know what dark energy is. The leading candidate is the cosmological constant, a property of empty space itself, an intrinsic energy density that does not dilute as space expands. As the universe gets bigger, there is more space, and therefore more dark energy. More dark energy means more push outward. The expansion accelerates. Other candidates exist: modified gravity theories, quintessence fields, exotic forms of energy that vary over time. We have no way to distinguish between them with current data. But regardless of which is correct, the basic phenomenon is the same. Space is being driven apart, faster every year. The numbers involved are striking. The current best estimate is that approximately 68% of the total energy of the universe is dark energy. The next 27% is dark matter. another mysterious substance that we cannot see directly, but that gravitationally influences galaxies and the cosmic microwave background. Only about 5% of the universe's energy content is ordinary matter, the stuff that stars, planets, and human beings are made of. We are minor characters in the cosmic story. The dominant components of the universe are things we do not understand and cannot directly observe. The visible matter, galaxies, stars, gas, dust, and everything we can see with telescopes represents only 1/20th of what is actually present. The rest is dark. This 5% of the universe's content that we have no way to directly observe, dark matter and dark energy, affects the cosmos in measurable ways. Dark matter holds galaxies together. Without it, the stars in galaxies would fly apart. Dark energy drives the expansion. Without it, the cosmos would expand more slowly and might even eventually collapse back together. Together, these dark components have determined the structure and fate of the universe. They are the dominant influences. The visible matter, including us, is just along for the ride. So when we talk about dark energy crossing galaxies past our event horizon, we are talking about an influence that immensely exceeds our own. We are watching the universe be reshaped by forces we cannot see, and one consequence of that reshaping is that our view of the cosmos is shrinking. As space expands faster and faster, more distant galaxies cross past our boundary of reachability. Their light, which was once making slow progress toward us, gets caught in faster and faster expansion of intervening space. Eventually, the light cannot win. It falls behind. The galaxy effectively disappears from our future view. This is happening right now. As you listen to this, somewhere in the cosmos, a galaxy is slipping past this limit. Its light, which has been on the way to us for billions of years, will not arrive after this moment. The galaxy is not destroyed. It still exists. It still emits light. But its light will never reach us again. From our perspective, that galaxy has become forever silent. We are losing galaxies all the time. It is hard to count exactly how many, because the process is gradual. Galaxies do not disappear in a flash, but rather fade out over very long timescales as their light becomes more and more redshifted. But the trend is constant. Every second, more of the universe slips out of our potential vision. This process is slow on human timescales, but inexorable on cosmic ones. In approximately 100 billion years, all galaxies outside our local group, the small cluster of galaxies that includes the Milky Way, Andromeda, the Triangulum Galaxy, and a few dozen smaller satellites will have crossed beyond our event horizon. The night sky, for future inhabitants of our region, will appear dark. There will be no visible distant galaxies. The cosmic microwave background, which currently saturates our entire sky, will have been redshifted so severely it will be undetectable. The vast structure of the cosmos, the trillions of galaxies, the filaments and voids of large-scale structure will all be invisible. By that point, the Milky Way and Andromeda will have merged into a single elliptical galaxy. Cosmologists sometimes refer to the future result as Milkomeda. It will be a single, large, old, elliptical galaxy surrounded by satellites that gravitational interactions held close enough to escape the runaway expansion. Beyond it, in every direction, will be empty space, truly empty. No light from anything beyond the local group will reach observers in Milkomeda. Any civilization that arises in the deep future of our universe will look up at a much smaller sky. They will see only their own galaxy, plus its nearest neighbors. They will have no evidence that the universe contains anything else. They will have no way to discover that billions of years before, there were trillions of galaxies stretching across an enormous cosmos. The information will be gone. The light will be gone. The proof will be gone. They will live in what looks like an island universe, a small group of galaxies floating in an empty void. As far as they can tell, that is everything. Imagine being a civilization in that distant future. You develop science, you build telescopes, you study the sky carefully, and you find nothing beyond your local cluster, no distant galaxies, no cosmic microwave background, no evidence of cosmic expansion. The universe, as far as you can tell, is just your single galaxy and its small companion cluster sitting in an infinite empty space. You would conclude, naturally, that this is what the universe is, a small, finite collection of stars and gas surrounded by nothing. You would be wrong. Your universe used to contain trillions of galaxies, but the evidence of them is gone. They have all moved beyond your causal reach. The light they emit can no longer reach you. The cosmic microwave background has been redshifted into nothing. The expansion of the universe is invisible because everything that could show it has moved past detection. This is not speculation. This is straightforward extrapolation of our current cosmological model. If dark energy continues to behave as it does today, and we have no reason to think it will stop, then this future is locked in. We are living, right now, in a privileged moment in cosmic history. The universe is currently rich and full of visible structure. 2 trillion galaxies spread across 46 billion light-years of observable space. We can map them. We can study them. We can derive the history of the cosmos from their light. We can know that we are part of something enormous. Consider how rare this position is. The universe has many phases. The brief inflation period lasting less than a second. The radiation-dominated era lasting about 50,000 years. The matter-dominated era lasting about 10 billion years. The dark energy-dominated era, which we are currently in, which will last for the rest of cosmic history. Within the dark energy-dominated era, there is a sub-window, a period when galaxies are still visible, when star formation continues, when the cosmos is still rich with structure. That window may last another 50 to 100 billion years before things start to seriously deteriorate. After that, the cosmos enters a long decline. Stars die. Galaxies become less active. Information about the larger universe becomes inaccessible. We are in that brief observational era. Within it, we sit in the first few percent. The universe is, by cosmic standards, very young. Almost all of cosmic time is ahead of us, not behind us. And almost all of that future is empty, dark, and devoid of the kinds of structures we observe today. This makes our era special. Not because anything important happens here on a cosmic scale the universe does not care about us, but because the cosmos is currently displaying its most photogenic features. Stars are bright. Galaxies are colorful. Cosmic structure is rich. Future eras will not have these things. Past eras did not have these things. We happen to exist in the moment when the universe is most worth looking at. This will not last. Astronomers 100 billion years from now, if any exist, will have no way to make these observations. They will not know about the Big Bang. They will not know that space is expanding. They will not know that there were ever galaxies beyond their local cluster. The cosmological information available to them will be vastly less than what is available to us. We exist at a moment when the full scope of the cosmos is still visible, when the past is still readable in the light, reaching us from distant galaxies, when the structure of the universe is still mappable. It is, in cosmic terms, a very brief window. The universe has been doing what it does for 13.8 billion years. It will continue doing what it does for trillions of years more. The window in which intelligent observers can see the cosmos as it really is, that window is narrow. We happen to be inside it. We are unusually lucky witnesses. Some cosmologists have called this the golden age of cosmology. Not because of advanced technology, though we have that too, but because of cosmic timing. The structure of the universe is visible to us in a way that it will not be in the deep future. Every observation we make today contributes to a record of what the universe looks like during a particular era. Future civilizations will not be able to verify our observations independently. The evidence will have moved beyond their horizons. But even now, even in this golden age of cosmology, we cannot see the whole thing. The vast majority of the universe is beyond our horizon. We see a small fraction. We deduce the rest. We will never know it directly. And tomorrow, more of what we currently see will become invisible. Slowly, imperceptibly, but inexorably, the cosmos is closing itself off. The view from Earth is at its most spectacular right now, and it will only get poorer from here. There is something almost melancholy about this. The universe is full of beautiful structures, galaxies, clusters, filaments, voids, and most of them are slowly being carried away from us. We are watching the cosmos slip away. Not all at once, but continuously. Every year, less of it is reachable. Every century, less is detectable. Over cosmic time, the universe we know will become invisible to whoever comes after us. We are observers at a particular moment. The universe is putting on a show. Most of the audience for the show is in the past. Future audiences will see only a fraction of what we see. They will look up at a smaller, emptier sky. They will have to take it on faith that the universe was once richer than what they observe. But of course, they will not even have that faith. The evidence will be gone. They will not know there was ever more. This thought is worth lingering on. Imagine you were a scientist in that distant future, a scientist on a planet orbiting a star in Milkomeda, the merged remnant of the Milky Way and Andromeda, 100 billion years from now. You have the same curiosity we have. You want to understand the universe. You build telescopes. You make careful observations. You develop theories. What can you discover? Quite a lot, actually. You can see your own galaxy. You can map its stars, its gas clouds, its black holes. You can detect the smaller galaxies that were once part of the local group and merged into Milkomeda over billions of years. You can study chemistry, physics, the formation of stars and planets in your local environment. But you cannot see past. Nothing else is visible. No distant galaxies. No cosmic microwave background. No filaments of cosmic structure. The sky beyond your local group is dark, empty. You might come up with theories. Perhaps the universe is small, just one galaxy floating in empty space. Perhaps the universe was always small. Perhaps it had a beginning that was different from what we currently believe. Perhaps there is no expansion, no Big Bang, no large-scale structure. Your theories would be wrong, but you would have no way to know it. The evidence to correct your theories would be permanently inaccessible. Future cosmologists will face this exact problem. The universe will continue, but the information about its past and its larger structure will be lost. They will live in their own bubble of vision, even smaller than ours, with no way to know what they are missing. The timeline of cosmic loss is worth detailing. We can predict, with reasonable confidence, how the universe will appear at various points in the deep future based on current cosmological models. In about 5 billion years, our sun will end its main sequence life and expand into a red giant, likely consuming the inner planets, including Earth. but that is a local event. The cosmos at large will look nearly identical to how it looks today. The Milky Way will still be a recognizable spiral galaxy. The Andromeda Galaxy will be approaching for its eventual collision with the Milky Way. Distant galaxies will still be visible. In about 4 to 5 billion years, the Milky Way and Andromeda will merge, forming Milkomeda, a single large elliptical galaxy. The ancient background glow will still be detectable. The observable universe will look much like it does now, just slightly more redshifted. In about 100 billion years, the universe will look very different. By that point, all galaxies outside our local group will have receded past our cosmic event horizon. The night sky will appear nearly empty beyond Milkomeda and its few satellite galaxies. The cosmic microwave background will be detectable only with extraordinarily sensitive instruments. Let us pause on this number. 100 billion years. That is roughly 7 times the current age of the universe. It is a long time on human terms, but it is short on cosmic terms. The universe has been expanding for 13.8 billion years. In just 7 of those lifetimes, everything we currently see beyond our local group will be gone. By that point, intelligent observers, if any have arisen by then, will have access to almost none of what we currently study. They will not see the ancient background radiation. They will not see distant galaxies. They will see only their own galactic neighborhood, isolated in apparently empty space. The fact that the universe is, or was, vast, that fact, will be lost to them beyond any way of recovering. In about 1 trillion years, the universe will be much darker. Star formation rates will have declined dramatically. As galaxies use up their available gas, many stars will have ended their lives, leaving behind white dwarfs, neutron stars, and black holes. New stars will be rare. The cosmos will be aging, dimming. In 100 trillion years, the last stars will be dying. The universe will enter what cosmologists call the degenerate era, a period when the dominant objects are stellar remnants rather than active stars. White dwarfs slowly cooling, neutron stars spinning down, black holes patiently waiting, few new stars forming. The cosmic show is essentially over. Beyond that, in time periods difficult to even write down, more strange things happen. Galaxies eventually disintegrate as their stars wander off. Black holes slowly evaporate via Hawking radiation. The universe becomes increasingly empty, increasingly cold, increasingly featureless. The total amount of structure in the cosmos decreases over time, even as the cosmos itself continues to expand. There is a name for the very far future of the universe: the heat death. The state when all energy has been dispersed evenly across space, when no useful work can be done, when no structures remain, when there is nothing happening anywhere, just empty. Expanding space, slowly cooling toward absolute zero. This is the long-term fate predicted by current physics, assuming the universe continues to evolve as we understand it. The heat death is, perhaps, the deepest version of the unobservable universe. Not just spatially distant, but temporally distant. Most of the cosmos's existence will happen during the long, degenerate eras after all the interesting astrophysics has stopped. We exist near the very beginning of cosmic history. The vast majority of the universe's future is empty, dark, and dull. We are in cosmic time, in the brief moment of light and structure. This is the fate of everything we see. The galaxies, the stars, the structure, all of it slowly fades into a darker, emptier, simpler universe. The information we have now about the cosmos is not just spatially limited, it is temporally limited too. The universe we observe is a snapshot of a moment in cosmic history. That moment is, in cosmic terms, fleeting. In this sense, we are privileged. We can still detect the ancient background radiation. We can still observe distant galaxies. We can still map the expansion of space. We have the information needed to understand the universe as it really is, at least within the limits of what is observable to anyone, ever. Future observers will be poorer in this regard. They will live in the same universe, but they will have access to less of it. The cosmos is closing itself off to them, one galaxy at a time. And to us as well, just more slowly. The first galaxies began crossing our event horizon billions of years ago. The most distant galaxies we observe today are seen as they appeared in the early universe. Their current state is forever lost to us. Other galaxies, closer to us, are still visible but slowly receding into invisibility. The process is constant. The cosmos is shrinking, from our perspective, even as it grows in absolute size. This is the strange dual nature of an expanding, accelerating universe. Space gets bigger, but observable space gets smaller. There is more cosmos, but less of it is accessible. The universe grows, but each observer's bubble of perception shrinks year by year. We are here at the brief window when our bubble is still relatively large, when we can still see most of what is currently within reach, when the universe is still readable as a vast structure full of light and information. This window will close. The universe will continue, but the view will get poorer. The information will be lost. The cosmos will become, for whoever survives in the distant future, a much smaller and lonelier place than what we currently observe. We started tonight at a wall, an invisible boundary in every direction, defining the edge of what we can ever know. Let us return to it now. That wall is not a prison. It is not a barrier deliberately placed to keep us inside. It is simply the geometry of an expanding universe combined with the finite speed of light. The wall exists because the cosmos is too big and moving too fast for any signal to cross it. Inside this boundary, we have 2 trillion galaxies, hundreds of billions of stars per galaxy, trillions of planets. A volume of space we have no way to fully comprehend, full of structure and light and matter and possibility. Outside this boundary, there is more. We do not know exactly how much. The conservative estimates put the unobservable cosmos at least 250 times the size of what we can see. The less conservative estimates put it at 100 sextillion times larger. The most ambitious estimates put it at infinite. Whichever is true, the implication is the same. We are inhabitants of a cosmos that vastly exceeds our perception. We have built telescopes that reach across nearly the entire observable universe. We have mapped the cosmic microwave background to extraordinary precision. We have catalogued trillions of galaxies. And all of this, every observation, every measurement, every discovery, covers only a tiny portion of what is actually out there. The unobservable cosmos dwarfs everything we know, possibly by a factor of hundreds, possibly by a factor too large to write down, possibly by an infinite amount. We do not get to choose. We just get to know that the cosmos is much larger than we can see. This is not, in the end, a sad thing. It is sobering. It places us in our proper position relative to the universe. We are not at the center of anything. We are not the largest thing. We are not the most important thing. We are observers at a particular location in space and time, with a particular bubble of vision, looking out at a cosmos that extends far beyond our reach. But we can know that it is out there. That is something. We have used the data available to us to deduce the existence of a vastness we will never directly experience. That is an achievement. To know about something you can never see, to derive its existence from measurements of curvature and uniformity and statistics, is one of the more remarkable things human beings have done. Consider what we have, just by being here at this moment in cosmic history. We have a universe that has existed for 13.8 billion years. We have access to light from nearly the entire history of that universe, including light emitted just 380,000 years after the Big Bang. We have telescopes that can see trillions of galaxies. We have theoretical frameworks that let us extrapolate from what we observe to what we cannot. We have, despite all our limitations, an extraordinarily rich view of the cosmos. Future observers will have less. Past observers had less. We are in a specific window, a specific moment, when the cosmos is at its most knowable, and even now, with all our tools and theories, we know that most of the universe is permanently past our perception. The amount we cannot know vastly exceeds the amount we can. This is perhaps the proper relationship between minds and the cosmos. We are not built to comprehend everything. We are not given a complete view. We are given a partial view of a sprawling cosmos that extends without limit in space and very nearly without limit in time. We make what sense of it we can. We map what we can map. We deduce what we can deduce. And we accept that some questions will not be answered, because the answers lie behind a wall we cannot cross. There is a particular kind of intellectual humility this should produce. Throughout history, humans have tried to understand the universe in terms accessible to our minds. Stories, myths, models, theories. Each successive understanding has been bigger and stranger than the last. We started with a flat Earth under a dome of stars. We moved to a round Earth at the center of celestial spheres. We discovered the heliocentric solar system. We discovered the Milky Way. We discovered other galaxies. We discovered the Big Bang and cosmic expansion. We discovered dark matter and dark energy. Each step has revealed a universe stranger and larger than what we previously believed. There is no reason to think this pattern stops. Future generations may discover things about the unobservable universe or about reality more broadly that would be incomprehensible to us today. We have, certainly, no privileged understanding of how big or strange the cosmos really is. We have a snapshot taken from a particular point in space and time of a process that extends past our perception. What we do know is that the universe is much larger than what we can see. The conservative estimates require it, the flatness measurements require it, the CMB uniformity requires it. There is more out there, much more. We simply do not know exactly how much more, or what it looks like in detail, or what kinds of structures fill it. And we know it is receding. Whatever the total size of the universe, more of it is becoming inaccessible every year. The cosmos is, from our perspective, a temporary phenomenon. The view we have now is the best view we will ever have. Future epochs will see less. The universe is, in this strange way, a flickering thing, enormous and visible to those who exist in the right window, less visible to those who come before or after. Consider what this means for the longer story of intelligence in the cosmos. Wherever conscious observers arise on Earth, or on the unreachable planets beyond our horizon, they have access only to whatever portion of the universe is observable from their location and era. We have a relatively rich view because we exist early in cosmic history, during the era when galaxies are still visible at extraordinary distances. Future observers will have impoverished views. They will see less. They will know less. This means the total amount of observable cosmic structure, summed across all observers in all eras, is finite. The universe is full of observers, scattered through space and time. Most of them, in the deep future, will see only their local cosmic neighborhoods. We are in the rare position of seeing far. The rare position will not last, but it exists now. There is something almost poetic about being in this position, not chosen by any cosmic process, not selected for any reason. We are simply here by chance during a particular epoch, with the right vantage point to see a universe that most observers across cosmic history will not see. Our successors will inherit a smaller view. Our distant cosmic neighbors live with smaller views in their own eras and positions. We have, briefly, the largest available view of the cosmos. Use it well. The wall is still there. Beyond it, the universe is still continuing. More galaxies, more stars, more space, stretching and growing and producing structure we will not witness. It does not stop. It does not end. It simply continues, past our knowledge, beyond our reach, past our imagination. We are a small bubble of vision floating in an unreachable cosmos. That is our position. That has always been our position. We just have only recently come to understand it. There is a final thought worth sitting with as the video closes. The universe was making galaxies and stars and planets and possibly life for billions of years before humans existed to notice. It will continue doing so for trillions of years after we are gone. We are not the audience the cosmos was performing for. We are not the reason any of this is happening. We are simply, briefly, here, aware of it, watching, and what we see is enormous. Even within our limited bubble of vision, we see 2 trillion galaxies, trillions upon trillions of stars, structures of unimaginable scale and complexity. We see the past stretching back nearly to the beginning. We see processes we did not invent and cannot change. We see, in short, a universe that does not depend on us in any way. This is, I think, a strangely comforting thought. The universe is not waiting for us to notice it. The cosmos is not concerned with our individual lives. We are not the protagonists of a cosmic story. We are observers at a window, looking out at something vastly larger than ourselves. What we are not is alone. Beyond our horizon, there are other observers at other windows, looking out at their own bubbles. There are versions of us doing what we do in places we cannot reach. The universe is full of consciousness by statistical inevitability. We just cannot meet any of it. The unobservable universe will go on. It will produce stars and planets and minds for as long as physics allows. It will continue, expanding, accelerating, evolving long after our local cosmic neighborhood has gone dark. The unreachable cosmos does not need us to witness it. It does not need anyone to witness it. It simply continues doing what it has always done in regions of space we will never see. We are a small bubble of vision, briefly aware of a much larger cosmos. That is our situation. That is our cosmic position. And tonight, having looked carefully at the limits of what we can know, we can settle into that position with a kind of peace. The universe is enormous. We are tiny. The cosmos has always been bigger than us. We are starting, only just now, to understand how much bigger. Lie back, close your eyes if you have not already. The universe is still out there. Most of it we will never see, but it is there, real, continuing, growing further away every second. Good night.